Hey, all you cool cats and kittens. It's time to learn some physical science. So, last video we learned about ionic bonds when an electron leaves one atom and goes to another, two ions form, and then that electric force attracts those ions together. And then we talked about metallic bonds. Now we're going to talk about covalent bonds. Covalent bonds do involve a transfer of electrons, but the electrons sort of spend time with both atoms, and some people describe it as being shared between the atoms. An ion is not formed whenever a covalent bond holds two atoms together. When two atoms are covalently bonded, that's really the best definition for what a molecule is. We've used the word molecule before kind of loosely, but technically a molecule is when things are covalently bonded together. All right, representing covalent bonds with dot structures. This is how you start to figure out how the covalent bond between two atoms works. So if we look at fluorine, for example, and we remember the dot structure for fluorine. Fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. So I just drew the dot structure for fluorine. And I'm going to draw this one like this. And I kind of have the benefit of knowing where I'm going with this, so I know where I want the lone electron to be. These other electrons are non-bonding pairs. And we're going to talk about how you figure out how many non-bonding pairs an atom has, but fluorine has 3 non-bonding pairs and then 1 extra electron in its valence shell that can participate in bonding. So when two fluorine atoms meet each other, these 2 electrons form a covalent bond, and you represent that with a line. So the line represents a covalent bond, and each atom, that's not how you spell bond. Each atom shares the 2 electrons that they had separately a while ago. Typically, when you're doing this, if you have successfully figured out how many covalent bonds and where they are to form a molecule, when you count the electrons for each molecule, you'll get 8. 8's the magic number for valence electrons that form bonds. Except the only exception is hydrogen and helium, because their outer shell only ever goes up to 2. If you have hydrogen and helium are happy with 2. Air quotes happy. Atoms aren't actually happy. Everything else goes up to 8. So fluorine, if you count the electrons on this fluorine, there's 1, 2, 3, 4, 5, 6, and then there's this bond. The bonds always count as 2. So 1, 2, 3, 4, 5, 6, 7, 8. This atom has 8. 1, 2, 3, 4, 5, 6, 7, 8. This atom has 8. When you can do that for all of the atoms in your group of or in your molecule, you've probably drawn the bonds correctly. All right, so let's try these as practice. If you want, you can pause it, see if you can figure out what it would look like, and then watch me do it. But I'll do it kind of quickly just so this video doesn't take forever. So hydrogen, there's 2 of them, so I'm going to write 2 hydrogen atoms. And then we got to go back and find a periodic table and figure out how many valence electrons are in hydrogen. Well, it's in the first group, so it's only got 1 valence electron. So go back to this page. We just put a single dot, put a single dot. The only thing that can happen here is that these single dots, or single electrons, form 1 covalent bond. So now this hydrogen atom has 1, 2, it's happy. This hydrogen atom has 1, 2, it's happy. And this molecule is done. We've drawn it correctly. It's a pretty simple one. Okay, number 2, H2O. There's some choices you have to make here. So since there's 3 different ways I could write these out. The order that you write them in could be anything like this. And then even more complicated is we'll find maybe they're not actually even in a line. Maybe it looks more like this or something crazier. Knowing where to put the atoms is not something we're focusing on right now. You have to learn a little bit more about what makes molecules have certain shapes, and we're not there yet. So when you're drawing these diagrams, I really just want you to focus on how many bonds there are and where the bonds are. But for H2O, this is the closest one to being right. Generally, nature likes things to be symmetrical. So remember that hydrogen just has one valence electron. If we go back and look at the periodic table and find oxygen, oxygen is over here. It's in group 16. So if you remember the trick, you just look at the ones place of 16, which is 6. So oxygen has 6 valence electrons. And then to figure out how many non-bonding pairs an atom has, there's really two ways. You can memorize that this group has 1, this group has 2, this group has 3, but I think the easier way is to just start drawing the dots and follow the rule that first space them out from each other, like this. One on top, one on the right, one on the bottom, one on the left. Now, if I'm only putting them on top, bottom, left, or right, if those are the only spots where I put electrons, when I start, I need to get to 6. I've only got 4 right now, so I have to put another one up here, then I have to put another one over here. It doesn't really matter where you put it. It will be a non-bonding pair. So 1, 2, 3, 4, 5, 6. Now I'm at 6. So it looks like oxygen has 2 non-bonding pairs and 2 electrons that are available for bonding. So it would actually be a little bit easier to draw these bonds if I put the lone electrons on the sides like this and the non-bonding pairs like this. Those are things you wouldn't necessarily know ahead of time. It just makes it easier to draw the bonds. Now, I got these two I have these 2 electrons available for bonding. I can connect them and form a bond. I've got these 2 to connect them and form a bond. The next step is to count. For each atom in this molecule, count the electrons it has to see if it's got a full valence. For oxygen, that's 8. It needs 8. So 1, 2, 3, 4, because bonds count as 2. 5, 6, 7, 8. So oxygen is good. Hydrogen, 1, 2, because bonds count as 2. The bond counts for both atoms that experience the bond. This hydrogen, 1, 2. So everything is good. This molecule's probably right, at least from the bond standpoint. Turns out later we're going to learn about polar molecules. Oxygen is actually, or water, actually looks more like this. No, there's nothing there. Because it's bent, and we'll learn why it's bent later. But that's something that you wouldn't necessarily need to know yet. Okay. NH3, ammonia. You got a nitrogen, a hydrogen, and you can put the other one either above or below, it doesn't matter. But we need to know what the dot diagrams look like. So hydrogen, they all have just 1 electron. Nitrogen, if you go find it on the periodic table, it's right here in group 15, so it's going to have 5 valence electrons. And if you don't remember how many non-bonding pairs it has, just use that trick where you start drawing, draw one on the top, draw one on the right, draw one on the bottom, draw one on the left. If you're not to the total you need yet, then you have to put a non-bonding pair in place. So 1, 2, 3, 4, I've got 5 now, so nitrogen has 1 non-bonding pair. Now it looks like I can draw a bond there, I can draw a bond there, I can draw a bond there. And if you count the electrons for each one, nitrogen has 1, 2, 3, 4, 5, 6, 7, 8, and then all the hydrogens have 2. It's happy. Carbon and hydrogen surrounding it. The hydrogens all have 1, and carbon, if we go look up carbon, carbon is in group 14, so it has 4 valence electrons. So we can put a dot here, we can put a dot here, put a dot here, can put a dot here, and then connect them. And if you count the electrons for each atom, everything's happy. Carbon has 2, 4, 6, 8. All the hydrogens have 2. It's happening. Okay, next page. Hydrogen is, like most things, special. It's got exceptions to things. Even though hydrogen is in group 1, and everything else in group 1, the alkali metals, all participate in ionic bonding, hydrogen almost never participates in ionic bonding. It almost always participates in covalent bonding, because it only has one shell of electrons, and hydrogen itself normally only has one electron, and if it just gains one more, then it's got a full first shell. So that makes it energetically more favorable for it to participate in covalent bonding. On the left, we kind of drew this in the dot diagram. Oxygen meets hydrogen. Oxygen has 2 electrons available for bonding. Hydrogen has 1. Hydrogen has 1. So they stick together and form that covalent molecule, water. Hydrogen itself, when you find it in nature, is actually a molecule of one hydrogen atom covalently bonded to another hydrogen atom. There's a few molecules like this. They're called diatomic. Di meaning 2. Atomic, diatomic, 2 atoms. And they're all, when you find a diatomic gas, it is 2 gas atoms covalently bonded to each other. So, how many covalent bonds can an atom form? Well, it depends on how many electrons it takes for that atom to have a full valence shell. So if we look at nitrogen, which was in group 15, that means it has 5 valence electrons. So if you draw the dot, you don't really need to draw the dot diagram, but let's do it. 1, 2, 3, 4, 5. How many more can it fit before it has a full valence shell? So, I mean, you can either think of full as meaning 8, except remember that hydrogen and helium, they're full with 2. Or you can look at the dot diagram. How many more dots do I need for it to be full, like I've been drawing? So you could draw another one there, you could draw another one there, you could draw another one there. So it needs 3 more to get to 8. Or if you knew right off the bat, if you knew there were 5, you need 3 more to get to 8. So 3 is the answer. Forget this for a second. We're going to come back to that. Yeah, I said this point up here already. If you look at carbon, carbon is in group 14, so it has 4 valence electrons. And when you draw the dot diagram for carbon, you have a dot on each side. That means carbon has 4 electrons available for bonding. That makes it pretty special. That makes, when you learn some more biology or organic chemistry, you'll learn that carbon kind of forms the backbone of most living things. A lot of organic molecules are made of big long chains of carbon, like this. Carbon. So you see, when you do this, the carbons can bond together and form like a chain, and then there's other things that can attach to each carbon because it has so many electrons available for bonding. Nitrogen only has 3, we said that. This is ammonia, this is methane. There's all kind of molecules that carbon forms with hydrogen in various numbers, and they're all called hydrocarbons, and you learn about those in organic chemistry, which is a class that people dread in college. It's not that bad, it's just a lot of memorization. Diamond is a unique covalent crystal structure. So diamonds are just made of carbon. All of the atoms in diamond are carbon. Most covalent molecules don't form crystals. Typically, if you see something that has a crystal structure, it's ionic, almost always. Here's an exception. A diamond molecule is when carbon forms 4 covalent bonds with other carbon atoms. So you get this chain structure like this, where each carbon is bonded to 4 other carbons, and then that one's bonded to 4 other carbons. So it's very structural, it's a repeating pattern. That's what a crystal is. And this is a single molecule. So this whole thing is one molecule. It's really rare that molecules are that large. You almost never can see molecules, but when they're huge and you can see them without a microscope, they're called macromolecules. And there's a few things that form those. Carbon's the most popular, or diamond's the most popular one. Multiple covalent bonds. So this is something we didn't have to talk about with ionic bonding, but with covalent bonds, it's possible that you can get more than one covalent bond between the same two atoms. So if you look at oxygen and you form the dot diagrams for oxygen, oxygen is in group 16, so it has 6 valence electrons. I'm going to draw them like this, just because I know where I'm going to draw the lines in a second. So if you want to make these oxygen atoms have a covalent bond with each other, you can connect these two, but then if you count to see if they have a full set, 1, 2, 3, 4, 5, 6, 7, it's not full. So it's not done. You haven't finished this molecule. It's not right yet. If you connect these two, now if you count 1, 2, 3, 4, 5, 6, 7, 8, it's full. This one also, 1, 2, 3, 4, 5, 6, 7, 8, it's full. That's called a double bond. A double covalent bond, but usually you don't say the word covalent. There's no such thing as a double ionic bond, so when you say double bond, everyone knows it's covalent. Carbon dioxide also does this. When you have one carbon and 2 oxygens, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and remember carbon has just 4. So these two could bond, and then these two could bond, and then these two could bond, and then these two could bond. I mean, and this looks messy. Normally it looks more like this diagram where the lines are nice and in between. But if you don't know it's going to look like that yet, it's hard to predict that. So if you count now, 1, 2, 3, 4, 5, 6, 7, 8. This oxygen is good. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. This carbon's good. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Remember, one bond counts as 2 electrons for this atom and also for this atom, for both atoms that are experiencing the bond. Nitrogen is a fun one. When a nitrogen gas is found, it is formed between 2 nitrogen atoms that have a triple bond between them. And when you draw their diagrams, you'll see nitrogen has 5 valence electrons. So if I draw, I'm going to space these out just because I know, here's the non-bonding pair for nitrogen. And normally I would put these on the top, the right, and the bottom, but I know I'm going to draw 3 lines connecting them, so I'm going to put them like this. So here's nitrogen, it's got 5, here's nitrogen, it's got 5. If I connect these two and count, 1, 2, 3, 4, 5, 6, still not good. Connect these two and count, 1, 2, 3, 4, 5, 6, 7, still not good. Connect these two and count, 1, 2, 3, 4, 5, 6, 7, 8. Now both nitrogens are good. It's a triple bond.